We're about to derive the derivatives of natural log of x, inverse sine of x, inverse cosine of x, and inverse tangent of x. Inverse functions. How are we going to do it? We're actually going to avoid the limit definition, kind of like we avoided it with the cosine. We're going to use some kind of fun tricks, actually. What's the trick to derive the derivative of natural log of x? It's to take this equation, e to the ln of x equals x, and differentiate both sides with respect to x. That equation is true. It's an identity for all x in the domain of the natural log function, meaning for all positive values of x. It's the definition of ln of x is why that's true, because ln of x is the number that e must be raised to get x. So if you raise e to the ln of x, you got to get x. It's true by definition. Though you might wonder, it is a question, does such a number really exist for an arbitrary positive x? The answer is yes, but that takes proof. So I'm about to differentiate both sides of this equation. d dx. Apply the d dx differential operator to both sides of the equation. However, there's a little bit of a problem here. In doing so, I'm assuming this is differentiable to begin with, and that I could apply the chain rule to it. Now, it does equal x for all positive x, so it is true. Since x is differentiable, this has got to be differentiable. But part of the assumption of the chain rule is that the inside function is also differentiable. I got to assume the natural log function is differentiable to begin with to even apply the chain rule here on the left side. Is this really going to be helpful? Because I don't know the answer yet. How could I apply the chain rule if I don't know what the answer is? We will see. It's kind of cool. This is a function composition. There is an inside function, ln of x, and an outside function, e to the x, right? When you plug a number into x here, you take the natural log first, and then you take e to that number that you get out from the natural log function. So again, the chain rule says, here it is again in abstract form. I've already used it once today, but in abstract form, the chain rule says to take the derivative of a composition, f of g of x is the inside function, f is the outside function. You take the derivative of f, the outside function, you plug in g into that, and then multiply times the derivative of the inside function. So again, in this expression right here, e to the natural log of x, the outside function, f of x, would be e to the x. And the inside function, g of x, would be natural log of x. We know the derivative of e to the x is e to the x, right? But the chain rule says plug in the g of x into that. G of x is natural log of x. Then multiply times the derivative of g, the derivative of natural log of x, which is what I'm trying to figure out. It's okay. We're pretending we don't know it yet, so we just write d dx of natural log of x. And if we differentiate the right side, x, we get 1. Oh, wait a minute. I could just solve this equation for d dx of natural log of x, divide both sides by e to the ln of x. We're done. Therefore, d dx, the derivative of natural log of x, is 1 over e to the natural log of x. Hey, but that's 1 over x. The derivative of natural log of x is 1 over x. That's interesting. A little strange, you might say, but true. It is true. Kind of amazing. The derivative of the natural log of function is a fairly simple function, 1 over x. X to the negative 1 power. Though technically that's only true for positive values of x. Actually, before we derive the derivatives of inverse sine, inverse cosine, and inverse tangent, let's also figure out the derivative of natural log of the absolute value of x, which is a function that's defined as long as x is non-zero. Ln of the absolute value of x equals ln of x if x is positive, and ln of negative x if x is negative. It's technically undefined when x is 0. Ln of 0 is undefined. Remember what the graph of natural log looks like? Goes down forever and ever. Got a vertical asymptote at x equals 0. So I guess according to this piecewise formula, we're going to get a piecewise formula here. We've just figured out 2 minutes ago that the derivative of natural log of x is 1 over x. What about the derivative of natural log of negative x, which, by the way, if x is negative, then negative x is positive. The opposite of x, we might prefer calling it. I guess I need the chain rule. Outside function is natural log, inside function is negative x. The chain rule says, once again, this is something you should think in your mind as you practice the chain rule. Take the derivative of the outside function, the natural log of x. The answer is 1 over x. But plug in the inside function into that, so I get 1 over negative x. That's parentheses there. And then don't forget, just like there's a g prime here, multiply times the derivative of the inside function. The derivative of negative x is negative 1. But hey, those negative signs cancel. I get 1 over x. No matter what x is, as long as it's not 0. X could be positive or negative here. And I get 1 over x. Huh. Interesting. And true. This is true. It's, again, technically undefined when x is 0. This is not an equality if x is 0, or you'd be dividing by 0. Their natural log of 0 is undefined. But if x is non-zero, you can do that. Okay, what about the derivative of inverse sine? We do a similar kind of trick. Natural log of x is the inverse function of e to the x. Inverse sine of x, also called arcsine of x, is the inverse function of sine over a certain domain, at least. We know sine of inverse sine of x equals x, at least for the values of x in the domain of the inverse sine function. What's the domain of the inverse sine function? You may not remember. This is true if x is between -1 and 1. That's the domain of the inverse sine function, not other values of x. I also could write this as arcsine of x. You should know that, and you should be comfortable with that, including for the gateway, to write it either way. I'm telling you right now. Do the same thing we did with the natural log. Differentiate both sides. Apply the ddx operator, which just means differentiate both sides with respect to x. On the right, I get 1 again. On the left, I got to use the chain rule again. Again, I'm assuming in using the chain rule on the left that inverse sine is differentiable, which is actually a problem at 2 points. It's actually not differentiable at the endpoints, though I'm not explaining why yet. The chain rule would give me the derivative of sine is cosine, plug in the inverse in the inside function, and then multiply times the derivative of the inside function. I'm applying the chain rule a lot today. Now solve for that derivative. Divide both sides by cosine of inverse sine of x. The answer can be written as 1 over cosine of inverse sine of x. But hardly anybody ever writes the answer that way, because there is a way to simplify it, to write it actually without trig functions, amazingly. How? You can use trigonometric identities. You also can think about it in terms of a right triangle if you like. It's a natural thing to do. It's not really a proof because we're just drawing a picture here, but let's imagine a right triangle. And let's imagine we're thinking about this angle in this right triangle. And let's pretend this angle right here is inverse sine of x. Can I do such a thing? Sure. Because in geometry, trigonometry, thinking about right triangles, we take the sine and the cosine and the tangent of angles. And therefore, if we take the inverse sine or the inverse cosine or the inverse tangent of numbers, we got to get angles. Inverse sine of x can be interpreted as an angle. It's an angle whose sine is x. Sine of that angle is x. But wait a minute. SOHCAHTOA. SOHCAHTOA. Sine is opposite over hypotenuse. This side divided by that side length. The answer's got to be x. So what does that mean? It means I can take this side to be x and this side to be 1. That's what it means. That's not unique. I could also take this side to be 2x and the hypotenuse to be 2. I could take this side to be 3x and the hypotenuse to be 3. I just want the ratio to be x. X over 1 is x. 3x over 3 is x. Might as well pick the simplest thing that I can think of. What do I want to do? I want to take the cosine of that angle. Ka, adjacent over hypotenuse. So I got to figure out the adjacent side. Pythagorean theorem. If I call this adjacent side, say A, the Pythagorean theorem says a squared plus x squared equals 1 squared. So A is the square root of 1 minus x squared. The cosine of this angle is square root of 1 minus x squared over 1, which is square root of 1 minus x squared. This is 1 over square root of 1 minus x squared. Hey, that's a function that's not defined when x is plus or minus 1, because you'd be dividing by 0. Right? If x is plus or minus 1, 1 squared and negative 1 squared are both equal to 1. 1 minus 1 is 0. You'd be in trouble. That's where this breaks down at the endpoints. This is true for x strictly between negative 1 and 1. What's happening graphically is this. If you plot the inverse sine function, where'd my Mathematica document go? Here we go. If you plot the arcsine function in Mathematica from negative 1 to 1, looks like this. And what's happening is at negative 1 and 1, the slope is approaching infinity. That's what's happening. Just like if you graph its derivative, the 1 over square root of 1 minus x squared, you get a graph that has vertical asymptotes at plus or minus 1. And looking at this picture, you should also compare the graphs and say, yeah, that orangish graph is giving me the derivative, the slope of the bluish graph. Near infinity, when x is close to negative 1 and 1, and in between, it's a positive slope. That's the smallest slope right there, because this graph's concave down slightly here and then concave up slightly here. That's where the slope is smallest. It looks like the slope at 0 is 1. And the reason is because when you plug in x equals 0 into this formula, you do get 1. It makes intuitive sense. What about inverse cosine? Once again, I could derive it the same kind of way. Same kind of method that I just did here with inverse sine. For fun, let's do it a different way again. I do mean for fun. For fun, let's do it a different way. What am I thinking of? Let's think about it graphically, the relationship between inverse sine and inverse cosine. In Mathematica, arc cosine. Look at those graphs. They look like they're related. Don't they? They look like they're reflections of each other across some horizontal line, not the x-axis, but a line up here. Where is that line? It's related to pi. It's, I believe, pi over 4. Y equals pi over 4. That constant is a horizontal line of symmetry between these graphs. Did you know that? I wonder what that would imply if you added these functions. Arc sine x plus arc cos x. You get another horizontal line when you add them. Inverse sine plus inverse cosine is always constant. What's that constant? Looks like it's double pi over 4. It looks like it's pi over 2, and it is. This is an identity, yet another identity today. Once you explore math enough, you see lots of connections. This is why math people like math. Lots of wild and unexpected things happen. Inverse sine x plus inverse cosine of x doesn't equal 1 for all x. It equals pi over 2 for all x between negative 1 and 1. That's an identity. It's always true. Effectively, in a right triangle, it's related to the fact that the sum of the angles in a right triangle is 180 degrees. Well, in any triangle is 180 degrees, but if you're talking a right triangle where one angle is a right angle, the other two angles add to 90 degrees, which is pi over 2. That's what you're doing. You're adding two angles in a right triangle to get to pi over 2 radians, which is 90 degrees. These are the two non-right angles in your right triangle. Once again, differentiate both sides with respect to x. But now I don't need the chain rule. Now I just use linearity. The derivative of inverse sine is, we just saw, 1 over the square root of 1 minus x squared. Pretending we don't yet know the derivative of inverse cosine, we write it like this. The derivative of pi over 2 is 0. Solve this equation for the derivative of inverse cosine. Subtract this from both sides. The derivative of inverse cosine of x is negative 1 over square root of 1 minus x squared. And that is true. And evidently, since the derivative of inverse sine is only true for x strictly between negative 1 and 1, this is also only true when x is strictly between negative 1 and 1, not the endpoints. These are facts. The derivative of natural log, inverse sine, inverse cosine, and what I'm about to do, inverse tangent, that you should know starting with next Monday's quiz. Should know for the gateway as well. Yeah, what is the derivative of inverse tangent? Use the same kind of trick as before. Tangent of inverse tangent of x equals x. That's actually true for all values of x, amazingly. There's no restriction on x there. X can be anything. The graph of inverse tangent is actually defined for all x. The graph of inverse tangent happens to look like this. It's got two distinct horizontal asymptotes at pi/2 and negative pi/2. That's the graph of inverse tangent. It is defined for all values of x. Once again, differentiate both sides. What's the derivative of tangent, though? Hey, we did this on Monday, right? Secant squared, remember that? Secant squared. Secant squared, that's the derivative of tangent. The outside function here, plug in the inside function, I'm using the chain rule now, times the derivative of the inverse of the inside function. And the derivative of x on the right side is just 1 again. Now divide both sides by secant squared. When you divide both sides of an equation by secant squared, it's the same as multiplying both sides by cosine squared. Because secant is 1 over cosine. It's the reciprocal of cosine. So dividing by secant is the same as multiplying by cosine. Dividing by secant squared is the same as multiplying by cosine squared. You can write the answer as cos squared of inverse tangent of x. Okay, can that be simplified? Let's draw a right triangle. Let's label this angle inverse tangent of x. Think about SOHCAHTOA again. Tangent is opposite over adjacent is what TOA says. The tangent of this angle should be x. So I can take the opposite side to be x and the adjacent side to be 1. Use the Pythagorean theorem to figure out the hypotenuse. You'll get x squared plus 1 squared. X squared plus 1. I now want to figure out the cosine of that angle. Oh, excuse me, square root of that. I got to take the square root to get the hypotenuse. I want to figure out the cosine of that angle and square it. So actually the square root's ultimately going to go away. Cosine is adjacent over hypotenuse. Adjacent side is this, 1. Hypotenuse is that. Square it, the square root goes away. There's the answer, which I actually more often write as 1 over 1 plus x squared. Either way is okay. And this turns out to be true for all x. Okay. A bunch of new derivatives to know for the next quiz and the quiz after that on next Wednesday and the gateway exam in 12 days. You need to practice. You're going to forget these if you don't practice. And by practice, I mean more than just trying to get your homework done and then going on to other things. I mean sitting down and practicing these on your own without, going beyond the homework. On your homework, that'll be due next Monday. It'll be another section and a half worth of homework, more about the chain rule and more about derivatives of trig functions. There are, other kinds of problems than just taking derivatives. I do have the extra problem solving videos that can help for that. We can also glance at some problems here. Some of them are purely graphical and symbolic. For example, like 58. Use this figure to, for example, find h prime of 1, h prime of 2, and h prime of 3, where h is f of g of x. No formula for f and g, just graphs, although you could figure out formulas for those. Think about it symbolically first. H of x is f of g of x. H of x is f of g of x. So wherever h is differentiable, its derivative will be related to where f and g are differentiable, f prime of g of x times g prime of x. That's the chain rule. So in particular, h prime of 1 is f prime of g of 1 times g prime of 1. So to figure this out, you got to figure out g of 1, and then f prime of that number, and then g prime of 1, looking at those graphs. G of 1, looking at this graph, g is the blue graph, g of 1 is 3. G prime of 1, being a linear function, is constant. It's the slope of this line, which is -1. G of 1 is 3. G prime of 1 is -1, because G prime of x is always -1. What's f prime of 3? I need the derivative of this graph, this black upside down V graph, at 3, which is the slope of this part of this line right here. Do rise over run. It looks like that slope is -2. This gives you -2 times -1, +2 for the answer. H prime of 2 is another question. That's f prime of g of 2 times g prime of 2. What's g of 2? Look at the graph. G is the blue line. G of 2 is 2. Times g prime of 2, which is -1. But f prime of 2 is a problem, isn't it? 2 is right here. F prime of 2 is the slope of this upside down V right there, which is undefined. This is undefined. So the answer is undefined. Probably shouldn't say equal undefined, but just it's undefined. Okay, so this is a combination of a graph and understanding how to think about things symbolically. Some problems are there's other types of problems. By the way, when you see these vertical lines like here at x equals 30, they mean take the derivative of the function, then evaluate at x equals 30. That's what this symbol means. Let's see, where is it? Sometimes you have to figure out where functions concave down, for example. What do? You got to take the second derivative and figure out where it's negative. Remember I said, in doing such problems, it's useful to factor as much as possible. Take those derivatives, factor as much as possible. There's another one I was thinking of here that I'm not seeing. Well, let's try one of these. 78. Just pure symbols. No equations or graphs. Given f of x with f of 1 equal to 2 and f prime of 1 equal to 5. Find g prime of 1 if g of x is f of x quantity cubed, and h prime of 1 if h of x is f of x cubed. These are two different function compositions here. With the one in part A, you're doing f first, that's the inside function, and cubing is the outside function. With this part B, cubing is the inside function, and f is the outside function. G of x is f of x quantity cubed. That means by the chain rule, g prime of x is what? Take the derivative of the outside function, which is x cubed. Its derivative is 3x squared, power rule. Plug in the inside function, so I get 3f of x squared times the derivative of the inside function. That's the chain rule right there. So g prime of 1 is 3 times f of 1 squared times f prime of 1. You only plug in your numbers after you've differentiated. F of 1 is 2. F prime of 1 is 5. 3 times 4 times 5 is 60. The answer is 60. On the other hand, h of x is a different function, f of x cubed. So now the inside function is the cubing function and the outside function is f. So h prime is f prime, the derivative of the outside, plug in the inside function, then multiply times the derivative of the inside function. So now if you plug in 1, please don't put stuff in your bags quite yet. We got 1 minute. You got f prime of 1 cubed times 3 times 1 squared. 1 cubed is 1. And f prime of 1 is 5. So the answer is 15. Okay, so you got to be able to deal with things symbolically. There are also application problems. Watch problem solving videos to help you with those if you need to. I do some applications as well. Okay. Have a good weekend.